folks that made this possible, the IRIS, Incorporated Research Institutes for Seismology, the Seismological Society of America, OMSI. I guess we've also been sponsored by Earthquake Tech, who are outside to talk to you about retrofitting if you live in this area and have a house that you might want to protect when the earthquake strikes. So I need to make a couple of introductory remarks. I wear a number of hats in my professional life. One of them is that I'm the USGS Southern California Earthquake Response Coordinator. And 12 days ago, we had the biggest earthquake in Southern California in 20 years. At 10:30 in the morning on July 4th, widely felt across Los Angeles and into neighboring states. And then less than 36 hours later, we had an even bigger earthquake, a 7.1, felt all the way up into Utah. And so still the holiday weekend, this has been my life for the last 12 days. I've barely thought about anything else. So I'm going to have to beg your indulgence. This talk is probably not quite as polished as it might have been if these two things had not blown up my life. But hopefully we'll still have some fun. The trivia contest was great. I feel like I could just go home and call it a night. But I won't. So anyway, these earthquakes in California were really very interesting, and it's something that scientists are going to be looking at for years to come, I expect. But what I came to talk about, and I tweaked the title a little bit, is what past earthquakes can tell us about future earthquake hazard facts and fictions. And basically, in keeping with the kind of fun and games theme, we're going to play Mythbusters. And the trivia questions, some of them that tripped you up, the good news is they're going to help you out here because some of them relate to what I'm going to be talking about. But basically what I'm going to do is give you a list of 7 statements that I'm going to ask you to think about, not even write down, but think about whether or not you think it's fact or fiction. And a couple of the answers you just got, so you get 2 points for free. But then through the talk, I will explain them a little more. So the first one is the church bells rang in Boston during the 1811-1812 New Madrid earthquake sequence. I think we know the answer to that. Quickly, second, which we also now know the answer to, the 1811-1812 sequence included the largest earthquakes witnessed in the contiguous 48 United States. 3, it's impossible to know the magnitude of an earthquake that occurred before the invention of seismometers. Fact or fiction? And I'm just going to ask you to keep a running tally, and then we'll see how we did at the end, and everything is made up and the points don't matter. So 4, okay, we're going to go a little bit far afield here. Recent moderate earthquakes in the central United States have been caused by hydraulic fracturing or fracking. Fact or fiction? 5, okay, the advent of widespread conventional oil recovery techniques is responsible for the increase of earthquake activity in the heartland. And that sounds a lot like the last one. But just think about it and think whether you think that's fact or fiction. They are worded differently, obviously. 6, with the increase in induced earthquakes, seismic hazard in Oklahoma is as high as in the western states. Fact or fiction. And the last one is, the big one is overdue in the Pacific Northwest. Okay. So, okay, let's get started. We are here in this nice high belt of hazard along the west coast, which is, I guess, the reason a lot of you are here today. I'm not going to be talking all that much about earthquakes in this area. I think people here have learned a lot before, and I suspect there are people in the audience who know more about them than I do, but I will be talking about them. So we saw this as a trivia question. Church bells rang in Boston during the 1811-1812 New Madrid earthquakes. And I'm going to talk about the New Madrid sequence a little bit. So it happened over 200 years ago. And if this slide, let's see what it does. This earthquake sequence left sort of a mark of Zorro in the boot heel of Missouri. You can see in the inset box where it is. Primarily ruptured two faults that scientists have been able to identify. There are a lot of accounts of the shaking effects from these earthquakes, and one of them from Charleston, South Carolina, from the largest New Madrid earthquake, is that the vibration of St. Philip's steeple caused the clock bell to ring about 10 seconds. So church bells rang in Charleston, South Carolina. There is more out there that you'll even find on USGS websites that say Boston. And so I have a theory about this, of where that lore came from. I think that Charleston at some point evolved into Charlestown, and that evolved into Boston. And that evolved into a myth that refuses to die. So if you take away nothing else from tonight, I would ask you to remember that church bells did not ring in Boston during the 1811, 1812 New Madrid earthquakes. So we're going to bust that one. And I wish I could put a stake in its heart and bury it. Okay, and this one also, you've heard about the 1811, 1812 New Madrid earthquakes were the largest earthquakes in the contiguous United States. So those earthquakes were portentous events. They generated felt shaking that extended over much of the country as it existed at the time. And these contours show what we call intensity. So that was a trivia question. Intensity is an old measure that rates the severity of shaking at any place where you are from a given earthquake. So magnitude is the size of the earthquake. Intensity is what's the shaking right here. And the scales have a similar range, so it confuses people. But intensity ranges from 1 for not felt up to 10 for the most severe possible shaking. And I'm going to be mentioning this, so just to give you an idea, intensity 6, well, intensity 5 would knock this water bottle off if we were hit by it now. Intensity 6 would be even stronger. It might start to cause light damage in vulnerable structures. So when we look at historical earthquakes, one of the main things we do is look back at what people wrote and described and use that to estimate the distribution of shaking. And so we look back at archival sources. And so at one point it was suggested that the New Madrid earthquakes were 8 3/4, which did make them the largest in the contiguous United States. One of the things I've done through my career is work on these earthquakes, look back at the original sources to see what people really wrote and interpret those. So here's an example of an account from Cincinnati of one of the New Madrid earthquakes that was so violent as to agitate the loose furniture of our rooms, open partition doors that were fastened with fallen latches, and throw off the tops of a few chimneys in town. So that's what someone wrote in Cincinnati, and if you just look at that, you say, oh, that's intensity 6 to 7. You're starting to damage chimneys. If you go back to the original source, which I found in the Library of Congress, it actually continues. And the person wrote, it seems to have been stronger in the valley of the Ohio River than in the adjoining uplands. Many families living on the elevated ridges of Kentucky, not more than 20 miles from the river, slept during the shock, which cannot be said perhaps of any family in town. Now that's more like intensity 4. So what this tells you is that there was shaking in the river valley where you have sediments, and away from that local effect, the shaking really wasn't as bad. So when you put all of that together, these big balloon contours that were first drawn in the 70s turns into a quite different view of the effects of those earthquakes. And the magnitude actually comes down from 8 3/4 to closer to low magnitude 7. The biggest earthquake in the contiguous U.S. for which we know the specific date, some of you know, was the 26 January 1700 Cascadia event, the last big one in this area. The date is known from the so-called orphan tsunami that was reported in Japan. So we know that exact date, and the magnitude has been estimated. I'll talk about that. Okay, so again, we are going to bust that one. Okay, 3, it's impossible to know the magnitude of an earthquake that occurred before the invention of seismometers. I've kind of sort of given you the answer, but that's the fiction. And in fact, there's a number of clever ways that scientists have developed to estimate magnitudes even without actual seismometer data. Having seismograms is for geologic observations of how the fault broke in the ground is the gold standard, but we can do quite a bit even without that kind of data. The trees can give us information. You may have heard the story of the ghost forest up here, forests that grew quite mature and then were sunk when the land went down. So that can tell us which tracts of land went down, and that can give you an estimate of magnitude. Tsunami modeling can give you an estimate of the magnitude if the tsunami heights were reported. Paleoliquefaction, I'll talk about some of these in the next slide. And then the shape of fault scarps. I'll talk about that. It may not be clear exactly what a fault scarp is. So one of the most direct kinds of information we have are these intensities where you look to see what the effects were as written down by eyewitnesses, and then you compare those to modern earthquakes that we know of the magnitude for, and you can back out the magnitude for a historic event. So that's one of the main ways. In some areas, paleoliquefaction is important, and this was important in New Madrid. Liquefaction is where you shake the ground so hard that some of the typically sandy soils lose their cohesion and vent to the surface. Basically, they're acting as liquids instead of solids. And if you fly around the New Madrid region, you can still see sand blows created by the 1811, 1812 New Madrid earthquakes. If you drive around when the crops are close to harvest, you can actually see patches of yellow where the crops aren't growing as well because there's these sand blows. So looking at that kind of information can give you an estimate of magnitude. Also, by digging down and looking for evidence of prehistoric sand blows, people have been able to put together a chronology of the prehistoric earthquakes. And so there's a complicated panel on that slide with the bars. This is largely work by geologist Tish Tuttle. But there's good evidence that the 1811, 1812 earthquakes were not the only ones that have occurred in that region, that we've seen similar sequences around 1150 AD, 900 AD, and then with sketchier evidence for earthquakes before that. Shape of fault scarps. This is an interesting one. So in some earthquakes, you have one side of a fault moving up relative to the other. And that can either be a thrust fault that goes, I don't know how well I sort of show up. But if you have a thrust fault that moves like this, one side moves up, or if you have a normal fault that moves away, it's more like this, but you can have a vertical offset. And right after earthquake, like the top panel that was in 1959, you have a nice clean break. And then over time, that break starts to erode, and you can actually describe that process of eroding the scarp with a mathematical function. So if you come along and measure the shape of the scarp, you can figure out something about how old it was, and then from the scarp, you can figure out something about how big it was. So the earthquake here in 1700, again, you may well know all this, the magnitude has been constrained largely from the tsunami modeling. How big did the earthquake have to be to get the tsunami that was observed in Japan? And the observations of coastal uplift, and the answer turns out to be a full magnitude 9 earthquake. Okay. So that one is pretty easy to bust. Okay, now let's move to the central United States. This is a story that kind of exploded into the news within the last 10 years. Recent earthquakes in the central United States have been caused by fracking or hydraulic fracturing. So let's talk about Oklahoma. This is a timeline of earthquakes greater than magnitude 3 in Oklahoma, starting in 1979 and going up to 2015. And then there's a map that shows the red dots are the earthquakes. And you can see how activity sort of went ballistic starting in around 2009. And one of the things I did, so that figure started in 1979. One of the things I've done is to take the clock back to the year 1900. There were some years of debate about whether or not these earthquakes really were induced, and some people were saying, well, earthquakes are always clustered in Oklahoma, and this is just another cluster. So I looked back at the catalog through 1900 and looked carefully, and it turns out that it's not just another cluster. It really is different from past periods. And oh, by the way, this little cluster in the 1950s, those earthquakes were actually induced also. So, yeah, that's a whole other topic. But to focus on fracking, the hydraulic fracturing involves this is going to get bad. Drilling into a production formation, so it's a sandstone that has oil that's in a tight shale formation where you can't just extract it with conventional methods. There's lateral drilling, and then fluids are injected to break the rock, and that process will release the oil. So by definition, you're creating earthquakes, you're breaking the rock. But the key point, and you start to pull oil out, the key point is that those production formations are fairly shallow. They're well away from the basement rock where you get natural earthquakes happening. And so it turns out that fracking itself does induce small earthquakes, but the bigger induced earthquakes, the more worrisome ones, overwhelmingly have not been induced directly by fracking. So I'm actually going to bust that one. But let's look at the statement that's worded a little bit differently. The advent of widespread unconventional oil recovery techniques or fracking is responsible for the many recent earthquakes in the heartland. You may be guessing by now where this is going, but you may also be saying, yeah. So, okay, let's look at this in a little more detail. The fracking involves injection of water into formations, and that essentially flushes the oil out. Now, wastewater has been an issue in oil production since the beginning, what's called salt water in the industry. Or wastewater is always a part of fossil fuel production. There's always a small amount, at least a small amount of co-produced water when you bring up oil. Sometimes there's a lot. So from the beginning, wastewater has been an issue in the oil business. If you go back to the early 20th century, people got rid of wastewater in various ways, like pouring it into storm drains and letting it go into the ocean, or just leaving it in open pits where it was left to evaporate. The thing is, it's not just water. There's a lot of salt in it, and there's also a lot of chemicals. So open pit disposal led to some unpleasant things like dead cows and lawsuits. So very early industry moved away from that and to deep disposal wells to get rid of this wastewater. So it's fairly salty, toxic stuff. And so the solution was to inject it deep into the ground to get below the aquifers and close to the bedrock depths where you get natural earthquakes. So what you're doing is you're pumping fluids down close to the basement rock, you're increasing the fluid pressure, you're making it easier for faults to slip, and overwhelmingly that's where the induced earthquakes are coming from. So fracking does not cause earthquakes per se, except to a minor extent, but the advent of fracking is responsible for this uptick in earthquakes because of the wastewater injection. So that one is confirmed. With the increase in induced earthquakes, seismic hazard in Oklahoma is comparable to that in the western United States. Fact or fiction? So this was a bigger story actually a couple of years ago. Oklahoma has, in recent years, really taken steps to regulate the industry, and the numbers of induced earthquakes have dropped off somewhat, which is great. But for a while there were figures like this. So the blue, this is the number of magnitude 3 or greater earthquakes in California in blue, and in Oklahoma in red. Somebody saw this and said, was it on purpose that California's blue and Oklahoma's red? I didn't make the figure, I don't know. But you can see that as of 2014, there were more magnitude 3s in Oklahoma than there were in California, which was pretty striking. And starting in 2016, the USGS put together one-year hazard maps. So usually a hazard map shows that the average long-term hazard, typically over 50-year type time frames, but it was felt that it was important to characterize what might happen within a year because there were so many earthquakes popping off. And this was the result. So it was split into two. In the east, you have the hazard dominated by the induced earthquakes, and in the west, you have the hazard dominated by the tectonic earthquakes. And you can see that these red zones are even bigger in Oklahoma than they are in the west. But, okay, this gets to the question of what are you showing on a hazard map? When you plot hazard, what does that mean? And it turns out to not be a trivial question. There's different ways you can plot hazard. And the way they did it, so again, this is 1 year. These are the earthquakes that are likely to happen on a short time frame. And they decided to plot the chance of having intensity 6 shaking. So not the chance of intensity 10, but the chance of something that's going to knock that off and do a little more. And by that measure, Oklahoma looks very red. And that's because they were having a whole lot of 3s and 4s and some 5s. And if you have that kind of earthquakes, that kind of rate popping off, the odds are pretty good that you're going to get up to intensity 6. But the odds are not equally good that you're going to get up to intensity 7 and 8 and 9 because you're not getting a high rate of the bigger earthquakes. And this is a figure I would have updated if I had had a little more time. But I went and found the magnitude 5 and greater earthquakes in the U.S. from 2009 to 2017. So these 5 and above now, the bigger events, not just the 3s and 4s. And you can see Oklahoma has had 4 events in that time. There was the Virginia earthquake, which was the earthquake that was felt by the most Americans ever. And I think I'm going to, there's one little thing I want to stop and say in a minute. But if you look at the west, that's where the bigger earthquakes are happening. And that's where we know that the rates are going to continue to be high. And so that's what really dominates the hazard. So this one is busted. Oklahoma has seen a whole lot of little earthquakes, but their hazard overall is not close to what we have here in California and the western states as well. Okay, so now I want to stop and just mention one interesting trivia question, kind of related to the ones you heard at the beginning. But this question is kind of continuing on, question about the 1906 earthquake. That was the earthquake that killed the most Americans. What was the earthquake in history that killed the second largest number of U.S. citizens? I heard an answer that's kind of along the right lines. Alaska. Alaska, no. Good guess, but no.
San Francisco?
No, that's the first. Northwest. Okay, you're getting warmer, ironically. 2010 Haiti killed 1,000 U.S. citizens. And most of them were Haitian American individuals who had U.S. citizenship, but then about 100 were people who were visiting in one capacity or another. I just wanted to, it sort of blows your mind. It is a global world out there. The biggest loss of life of Swedish citizens in a natural disaster was the Indonesian event. So that's a minor tangent. But let's come back home and talk about what you're all really interested in, and that's the big one, and whether that's overdue in the Pacific Northwest. So I'm guessing you've heard about this in recent years. Another kind of minor tangent, California's earthquake hazard was really apparent in Northern California starting in 1903, and then in Southern California starting with the Long Beach earthquake. And that was really fortunate because California's big building boom happened after earthquake hazard was recognized. After 1933, there were statewide building codes that were enacted real fast. They aren't as good as they are now, but there were basic building codes, and unreinforced masonry basically came to an end after 1933. The Pacific Northwest had a very different history. There have been earthquakes here, but nothing that really got people's attention like 1906 or even 1933, which has allowed the region to grow before the hazard was recognized and the building codes were put into place. And yeah, so when I was in graduate school, which was a while ago, but not quite the Cretaceous, it was still debated whether or not the Cascadia subduction zone would produce great earthquakes. Some people thought that it was aseismic, that the subducting slab would just sink gradually without producing earthquakes. And that school of thought evolved since the 80s, so that's really just in the last 30 years or so, that recognition. But yes, there really is a really big earthquake hazard here. And since that time, a whole lot of results have come out, and it's really impressive how much is now known, including a timeline of events. And I was hoping this can sort of be seen, at least in general. I know you can't see the numbers, but mostly looking at what's called turbidite currents, so pouring offshore, you can see these layers of sediments that were churned up that are thought to have been caused by major earthquakes. There is some debate that maybe some of them can be caused by storms, and so that's the source of uncertainty in all of this. But by looking mostly at those layers, people, and Chris Goldfinger has led this, have put together a timeline going back sometime in the past. And this goes back to almost 8,000 BC. These reds are large, very large earthquakes, magnitude 9-ish. And then there's some ones in here that are more like 8. We are out here, so it's been 319 years since the last big one here. And it's now known that, or believed, that different parts of the Cascadia subduction zone can have somewhat different behavior. So from Coos Bay toward Eureka, that segment seems to produce a big earthquake every 230 years or so, whereas Newport to Coos Bay, it's more like 350 years. And then the whole ball of wax may go Oregon and Washington about every 600 years. So there's been some concern that, well, it's been 300 years, maybe we're overdue for the earthquake. So I want to look at that overdue word. And to do that, I'm going to go back to California and the San Andreas. because it's useful to make the point, given the history we've had. So this is a complicated slide. It shows Southern California. There's an inset region that you can see there. Down here, if you can see my cursor, I don't know if it shows up. And then this is the fault. The San Andreas comes down, and then it kind of splits into two. And there's quite a bit known about earthquakes on this fault. The big stretch of the central San Andreas broke in 1857. So over 150 years ago, and then to the south, we haven't had a big earthquake since 1700. There's been a lot of work similar to that in Cascadia, using different methods to establish how frequently earthquakes occur. And it's been a while, quite a few years since the last big earthquake. So there's been a tendency to say the big one is overdue. Let me just skip to this idea of overdue and what we can say. So this is just from the last week or so, headlines that came out from CNN. Seismic activity along the San Andreas fault line could trigger a devastating earthquake in California by 2030, so in 10 years. This is this year. Here's another headline. Scientists call recent California earthquakes a final warning. This was 1992, after there were big earthquakes in the California desert. And here's another headline, earthquakes to shatter Southwest in 10 years, noted seismologists said. So if you can see the date, this was in 1925. So overdue, 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 starting in 1925 and continuing for 90 years, and that earthquake hasn't happened yet. So what that tells us is we can't say that earthquakes are overdue because we don't know when they're due in the first place. They're not babies. They don't have due dates. And these plots may look ominous, but there's a lot of uncertainties. There's gaps looking back, the long periods when earthquakes, there's no evidence for big earthquakes. So we know they're inevitable. That's the bad news. This zone is going to go again. The southern San Andreas is going to produce a big earthquake again. If you're living in these places, it's something you have to be aware of. It's something you have to prepare for. But we really don't know. This tendency to say overdue, something's going to happen in the next 10 years, it really goes beyond what science can say. So I'm going to suggest that one is busted. It's possible it could happen any day. It could happen tomorrow. It could happen 300 years from now. But we just can't say overdue. So we can now, again, see how we did. So seven statements. Church bells rang in Boston, fiction. The 1811-1812 sequence were the biggest earthquakes ever witnessed in the contiguous U.S. Fiction. It's impossible to know the magnitude of an earthquake that occurred before the invention of seismometers in essentially 1889. Fiction. Recent moderate earthquakes in the central United States have been caused by hydraulic fracturing. Fiction, as worded. The advent of widespread unconventional oil recovery techniques is responsible for the increase in earthquake activity in the heartland. That's fact. With the increase in induced earthquakes, seismic hazard in Oklahoma is as high as in California. Again, fiction. And the next big one is overdue in the Pacific Northwest. I will say that that's fiction, but it could happen anytime. So, with that, I'm wondering, a show of hands, who got 7 out of 7? 6? 5? Okay. So I want to end with one more slide and a comment about the business of science communication. And it was striking to me. I gave a talk like this in Kansas City. It was even more focused on the central U.S. And people who show up at talks like this, you are a well-informed bunch. you come out on an evening and you hear a talk like this. I'm guessing you've heard other talks generally, and you look for information, and yet there's still a lot of these misperceptions out there. And I put a big part of the blame for that on my professional community. That scientists are supposed to be smart people, but we're not doing a good job of talking to people in English in ways that's accessible to people who are not scientists about the issues that are important for their lives. That's something we need to work on. There's my last slide. But I think science communication is really a three-way street. That the scientists need to communicate, people do need to listen, but there's also a very big role that organizations can play to help facilitate that communication. So on that note, I would like to end with another note of thanks to IRIS, to SSA, to OMSI for making this talk possible, and to all of you for showing up tonight. So with that, I'll be happy to take your questions.
So there are a lot of you, and me and one volunteer, so a couple requests for you. Make sure to raise your hand high so we can see who has a question. I see you right there. Wait till you get the mic so everyone can hear your questions. And then when you get the mic, speak into it closely. Can't really hear you out here, but we can hear you up here. Sound good? Cool. I'll start with you right there. And my partner will make their way in shortly.
And if people need to take off from the cool.
So I don't have to stand up. Okay, good. So previously, I heard a talk here from PSU Dr. Seismology, I believe. And we spoke about the Wanda-Fuca plate, and you haven't mentioned that. And so I thought that was our very own, I don't know, up here in the Northwest. But that is where he said the 9.3 was going to come from.
Yeah, that's a good question. If I had had a little more time to prepare, I probably would have thrown in some more slides. But so what's happening in California is you have two plates that are moving past each other sideways. And then you get up to Mendocino, and that part of the plate boundary ends. And then you have the Wanda-Fuca plate offshore that's diving under the continent. So you've got one of these kind of zones, and that's the setting that gives you the biggest earthquake on the planet. Because the size of an earthquake is fundamentally determined by how much fault breaks, how big the patch is, and how much it moves. The San Andreas is a skinny little fault. So it's long, but the earthquakes only go down 15 kilometers, so they can't get much over 8. But if you have a big, deep fault and it's wide, then you can get up to magnitude 9. So it's the subduction of the Wanda-Fuca plate under the continental crust that's giving you that hazard. And then you also have secondary faults, which are important to remember. So the earthquakes that we've seen in California and Northridge, that was only a 6.7, but if something like that hits close to where you live, that is going to be a big one for you personally. So there's faults in the crust that can have these moderately large earthquakes, and that's a serious hazard as well. And those are more frequent. The really big ones may be every few hundred years, but the pretty big ones might be every 50 years.
Nowadays, with the advent of machine learning, I would expect that you will be able to build up more correlation models to say that what are the likelihood of earthquake. I wonder how much fracking make a positive impact to the science where you can build out a better causal model to understand that, so that it's not just observational correlation, but also causal correlation. Thank you.
Yeah, that's interesting. I think people have learned a lot about induced earthquakes. One of the issues is they are different. They're being driven by fluid injection. So, how much we can lose. We might learn something about what kind of pressure changes can induce earthquakes, but because they're different, they're not going to tell us so much. But machine learning is interesting. People are using it in seismology to do a number of things, including better locate little earthquakes and detect little earthquakes. And maybe people have been, I didn't talk about earthquake prediction, which is another big can of worms. I actually wrote a book on that, predicting the unpredictable. And people have been trying for a very long time to find patterns. Reading the tea leaves, looking at the earthquakes popping off and saying something about what's going to happen next. And it just hasn't panned out. There's been a lot of promising leads, but then nothing was really borne out as people looked more carefully. So maybe, scientists don't know everything, and maybe machine learning will find some patterns that exist that we just haven't seen yet.
That went all the way in the back.
Thank you. You mentioned about using ghost trees and several other techniques to measure pre-seismograph quakes. Right? So now that we have lots of earthquakes that are measured by seismograph, can you use the data to fine-tune the good old tool to make the old results better and hence understand the faults better?
I'm not sure where to look. My thumb is not here. Okay. Yeah, no, that actually is what people have been doing. You have earthquakes recorded on seismometers, so you know very well what the magnitudes are, and then you know what their effects are, how widely they were felt. So you use those just for calibration. If you look at older earthquakes, are they bigger? Are the effects the same as something that's happened more recently? The problem with that, so it's definitely an important approach. The problem is a lot of times the historical earthquakes are bigger than anything we've seen in recent times. In New Madrid, we haven't seen any earthquake like that since we've had seismometers. So you're kind of extrapolating. You've got calibration events that are smaller. And New Madrid was bigger, but it's tricky to say how much bigger it was.
That one here.
Okay, so I just want to go back to that concept of due or overdue and how we communicate that to people. So when I talk to people, I say that I don't say we're overdue because I agree we don't know the due date. But what I do say is that by averages, we are overdue. Because when people hear we might not have it for 300 years, they go, oh, great, I don't have to take this seriously.
Yeah, I get your point. I mean, what I say, and we deal with the same thing in California, where we are waiting for this big one out there. The point that it could be tomorrow. And this is the fine line of vanishingly fine line of communication that we've somehow got to walk. Because the problem with being breathless about the overdue statements is that eventually people might get their attention, but they're going to start to tune it out.
So I feel like that's where the difference is between like California and Oregon, where we don't have these sort of trial runs to help our building codes or whatever. And so I guess we work together, it's the idea that something's busted because it's not overdue. We really don't want people to relax about that in Oregon.
Yeah, okay. That's a good point. No, we don't, absolutely. We don't want people to relax. But yeah, it is finding that right message that, that's a very good point, thank you. So I hope everyone heard that. When I say, I don't think you can say it's overdue, but that doesn't mean it's 300 years away. Stop worrying about it. We want everybody to be aware of that possibility and to worry about it enough to go put the valve on your gas main so that it'll shut your gas line off. There's a big earthquake. That could save your house from burning down. If you've got cripple walls, go, we enforce those. I did that for my house when I moved into it in 1998. Having the water, having the emergency supplies, those things, making sure nothing is on the wall above your bed that's going to fall on you. And all those things really are going to make a difference for your safety and your family.
A question in the center, all the way back.
Well, firstly, I want to say that I appreciate that on your Cascadia timeline you have first wine made as a significant date. I'm from Canada, and we're on the west coast of BC. I'm curious, one, if we're on the San Andreas Fault as well. This is a new topic for me. And then when we drive along parts of the coast, there are signs that warn us that we're in a tsunami zone. And I'm curious or how far that extends down. Are you also on that down here in Oregon and down into California?
Yeah, so California, the San Andreas ends at the Mendocino, we call the Mendocino Triple Junction, so from Oregon, Washington, and then continuing off of Vancouver, you have the subduction zone. So yeah, you have off of Vancouver, in Vancouver Island, you have that same hazard, and then Canada gets a little bit complicated, and I'm not the best person to talk about it. What happens above Vancouver Island is eventually when you get up to Alaska, there's another massive subduction zone where you get these, again, the massive subduction zone earthquakes, including one, most recent one in 1964. But definitely up just as far as Vancouver, you're kind of in the same boat as Oregon and Washington.
And up here, on your right.
Hi, I have two questions. One was the slide about the Ohio River Valley showing up all of the little ones, and I wondered if those were connected to the waterways specifically, of when you re-looked at the data, as opposed to the mountain ridges, and taking from that, looking at the Willamette River versus the Columbia River and the waterways here. Is there any extrapolation of how the effects of earthquakes happen along river valleys as opposed to basalt, or like gravel outwash plains rather than basalt hills?
Okay, that's a really interesting question. I think you mean the slide that showed the little boxes. So those are, I maybe didn't explain that very well. Those are the locations where we have reports so we can assign intensity. So those aren't actually little earthquakes, but that's where, instead of drawing the contours on this map, I put squares where you have, say, Louisville, Kentucky, and someone said, Zachary Taylor said chimneys were knocked down. And
I wondered if they were on waterways.
yeah, no, that's actually, there is a suggestion, if you look at where earthquakes happen in the central eastern U.S., the fault zones are aligned often along the major riverways. And so we still don't entirely understand that. It may be that the faults are there because the rivers are there, or vice versa. So there is some association between major riverways and fault in some cases. I'm honestly not sure of the situation in this area.
The second part was to extrapolate from how it affects on like the West Hill, which is basalt, versus the Willamette or the Columbia, alongside of the river.
We know that these softer sediments can amplify shaking in a lot of cases. So if there is an earthquake, you're generally better to be on the harder rock than to be on the softer sediment.
One in the back center.
So I'd like to take this question a little bit back to the tsunami hazard zones, which we do have designated along the Oregon coast. But this question is more so when you are driving along the highway and it says you're entering and exiting a tsunami hazard zone, what is the certainty that you are actually entering and exiting in those locations, or if you are told that you're exiting the tsunami hazard zone, what is the reliability there? What is that based off of?
That's a really good question. In general, we can take, like, say, okay, what happens if a magnitude 9 earthquake happens? We can calculate how big we expect the tsunami to be and how far it would come inland. Those calculations are pretty good. But there's some uncertainties in the Hough earthquake in Japan in 2011. They had planned for earthquake like low magnitude 8. They built the seawalls, and then the tsunami was very much bigger. So I think in this area, I think people have a handle now on what the maximum earthquake size is. I think they would have a pretty good sense of how big the tsunami is expected to be. Certainly, if you're right along the coast, that's the big concern. If you feel something, you're going to need to get to higher ground if you can. Exactly how precise it is, my guess is that they err on the side of caution. But beyond that, I can't say.
But someone up here at the very top.
Yeah, my question is, when was the last time and what magnitude of an earthquake hit Metro Portland? Is that in history?
I don't know. I know there have been some up in Seattle in 2001 and in 1959. Maybe someone here knows.
It's like 6.0 in 2000. It was 6.0 or something about that in 2000, 2001.
Yeah, but there haven't been a lot of significant events up here.
Yeah. Any more questions?
I see that people are starting to vote with their feet. Thank you for.
I have one question I can answer.
I'm walking down to one. If you wait a moment.
Oh, okay. I'll answer that because it's a great question. Did the Mississippi River reverse course during the earthquakes? Who thinks yes? Who thinks no? It sounds like a myth. It's actually true. There was one of the earthquakes had a thrust fault, so it came up like, let me get it right, like this, and it actually pushed the flow of water back temporarily, and then it was.
Hi, I experienced an earthquake in Portland, Oregon in the late 1950s.
Oh, okay.
I don't know what magnitude or intensity it was, but it happened.
Okay, yeah, I believe you. I'm just not up on it. There's a hand here who's been up here a lot, but yeah.
I just wanted to recommend a book.
Okay.
It's a field guide to the San Andreas Fault by David Byrne, B-Y-R-N-E, and it takes a tour going from the Salton Sea all the way up to Eureka, and it takes it day by day going south to north. It's a self-published book, so it's probably not widely distributed.
Actually, I've read a couple books. One of them was kind of developed in California, so it's an earthquake tourist guide, and the idea is it's some of the San Andreas, but where you can go in California to see what faults look like. And
we've actually seen buildings being torqued by the faults.
yeah.
And we drove it from the Salton Sea all the way up to just below San Francisco.
Yeah, that's great.
At first you don't recognize anything, but after a while you start to see areas that are just really tortured. Up near the Hough Pass and all that, where the two big faults intersect.
That's great that you did that. Faults, some of those pictures you saw, those were Hollywood, the cracks in the ground. Looks like that.
I got a question down in the front left.
Over here. So I've really enjoyed your books, and I'm wondering if you're planning on writing anything new?
I'm finishing one. That's looking, it sounds boring, but it's really not. I'm looking at the period between 1906 and 1933 when the severity of earthquake hazard in Los Angeles was debated, and there were business interests that were trying to downplay earthquake hazard. There were geologists who were trying to start earthquake monitoring programs. It's really an intertwined biographies of two geologists who are kind of embodying the debate. So it's really a character-driven story, but I think it's pretty interesting that the two characters, the two geologists, were fascinating individuals. So yeah. What is it called? The Great Quake Debate.
And then I have a question over here on your right.
Over here. Yeah.
Yes.
I'm sorry about being repetitive, but I want to get back to the overdue question that I had before because I thought it was a really interesting topic. Particularly because when I heard you say that, I felt, I spent the last maybe 3 or 4 days looking at Amazon, trying to get walkie-talkies, preparing for when it's going to happen, and looking at insurance for my home. And so hearing you say that, I really felt a very positive feeling. And then, but then the question of what to do with that information is really relevant. And and at the end of your talk, you said that you felt that there was responsibility in the scientific community about how we communicate these things. And I feel like part of the problem is that we rarely do hear directly from the scientific community as an audience. And so I'm wondering, you're here talking to an audience and you're choosing to bust this myth. And so I'd like to hear you say why do you think it's important that this myth is busted?
See, I think we have to find the right balance. And yeah, no, it absolutely is not the message that I want to convey to not worry. Because you saw that map at the beginning, and maybe I'll get back to it. The hazard map for the United States has that ribbon of red that runs right up and down the coast, and that's a hazard that we live with and that people have to take seriously. I see a problem with these breathless, overdue statements. It goes beyond what scientists can say. So let's see if I can get it back this one. Well, it'll take a second for some reason to come up, but you'll see the hazard map, and this was produced, the most recent hazard map by the USGS. That hazard's high. I don't think scientists should be standing up and saying things that aren't true, that aren't supported, and overdue goes beyond what we can say. And that's just a purist point of view. But then, again, there's this problem of getting people's attention and keeping it. And if you're saying 10 months pregnant and you've been saying that for 30 years, people start, and that's true, in California, people have been saying the San Andreas Fault is 10 months pregnant. In the 70s, in the 80s, in the 90s, people start to tune that out. So again, it's about finding the right message. I think saying what we can't say. We can't say it's going to be in the next 10 years, but it's possible. It's fair game. And then emphasizing what we do know. That's my take on it.
So does that mean, would you rather advocate for a sort of like just a yearly probability of having it as a communication?
Well, I would advocate for this map.
Okay.
You're in the orange or you're in the red, and it's something you got to take seriously. And it's not just the big one. It's that 6.5 that might be near you. That might be worse than the big one that we're all, the boogeyman that we're all fearing out there.
Another one in the way back. So you talked about fracking as like a possible way of how earthquakes could occur, and you busted that myth. But are there any other man-made, induced things that occur that could also increase the causality of earthquakes?
Yeah, there are a few. It turns out that actual oil production, pulling oil out of the ground, can cause earthquakes because you're You're just taking mass out of the ground, so things can shift around. That's a whole other talk. Mining, large-scale mining, can sometimes cause earthquakes. I feel like I'm forgetting something. But, okay? Yes, thank you. Reservoirs and dams. If you impound a large reservoir, you can induce potentially significant earthquakes. Thank you.
I got midway here.
Hello. For one, I'd like to thank you for this tonight. I've enjoyed your talk, but one question I had was how closely related you might believe seismic activity to be to volcanic activity.
You guys are asking good questions. In some cases, it's definitely related. Like if you have an active volcano, you get earthquakes there. When Mount St. Helens erupted, it started with an earthquake sequence. So as you build to an eruption, you definitely have earthquakes associated with that. In some cases, big earthquakes can trigger volcanic activity nearby. Not over like global scales, but pick up in Alaska if you have a big earthquake. Sometimes that is an interplay with local volcanoes. So you can get some interplay, but it's not like people sometimes hear that a volcano is erupting, in Italy, and then there's an earthquake in California, and there's no connection with anyone who's ever found between distant activity like that.
You got one in the way back in the dark. Can you explain what the measurement system is? So you hear these numbers like 7.4, 8. What exactly does that mean? What gets something to move up the scale, and is it linear? So if something is a 8, is it necessarily twice as big as like a 4? I have no idea how that actually works.
I love that question because magnitude numbers don't mean anything. It's not watts or joules or any physical unit. So Charles Richter defined the scale in 1935 as an arbitrary set of numbers, and it's based on it was based at the time on the peak shaking recorded on a certain instrument, and he just tuned the scale to give a sensible range of numbers that you could kind of communicate to people. He tuned the scale so that magnitude 0 was the smallest earthquake that he calculated could be recorded at the surface under normal conditions, and still today that's true. It was a good calculation. It's open-ended, so it doesn't end at 10. The biggest earthquakes possible on the globe might be somewhere around 10 because there's only so much fault size on a finite planet. But those numbers don't mean anything in terms of physical quantities as defined. It's just 3 is a small shock, a 6 is a moderately, maybe locally damaging shock, and 8 is an earthquake like 1906. So the only meaning that those numbers have is what Charles Richter defined in 1935, and all later magnitude scales have improved our ability to estimate those numbers, but we're still using that same scale. And then we've developed other more physical ways to measure the size of earthquakes. So looking at the energy released, for example, or the size of the fault that moved. The magnitude scale is not linear. You may have heard that it's logarithmic. So all that means is that from one earthquake, one magnitude to the next, it's a factor of 30 in energy. So or 2 magnitude units is a factor of about 1,000. So a magnitude 7 releases 1,000 times more energy than a magnitude 5. What was I going to say about that? There's an important point that if you think about the peak shaking, so how strong is that, the worst jolt that you feel, that's not the same factor. It's not a factor of 30 from a 5 to a 6. And so if you're right on top of a 5, that peak whoomp can be pretty high. and this gets into a longer explanation that you probably want me to give. I can try, since everyone's still sitting here. So if you have a very big earthquake, well, if you have an earthquake, the size of the earthquake reflects the size of the fault that moves, and that sort of determines the overall energy. But the actual peak shaking, if you imagine, instead of an earthquake, imagine a train going down a track and there's a clickety-clack, and that clickety-clack is released all along the fault that moves, and that's what controls the peak shaking. So the clickety-clack is not that different in a very big earthquake than a pretty big earthquake. It's like the train doing its thing, and you get that clickety-clack. So that peak punch isn't too different. That was probably way more confusing than sorry.
I've got one midway back.
Can you go back to the slide with the history of low intensity and high intensity over time?
Sorry, which one?
The one that covers 10,000 years or whatever it is.
The one towards the end.
Yeah.
Okay. This presentation.
That one, yeah.
Yeah, and I mean, getting back to the whole question of hazard, like, you know, this plot tells its own story in terms of. Sorry, go ahead.
Well, the Hough Bay to Eureka has a certain intensity, and it happens like every 250 or 300 years, and it's got geographic area, but the 600-year one does not have a geographic area. And I heard before that California and Southern Oregon is going to be a less like an 8 maybe magnitude, whereas up north of Coos Bay and into Washington there might be more likely a 9. Can you comment on that?
Yeah, so the 1700 event was quite big. It was Oregon and Washington and spanning the zone. That gets you the 9, but it's also the zone isn't going to go like that every time. We've seen the turbidite record. So there's the part of the zone could go separately. So you could get these earthquakes closer to 8 that are on these different stretches of the fault. So it might be an 8 here, and then down the road, the 9 that is both sections of the fault. So it's not like certain segments of the fault always produce a certain size earthquake. You can get this part of the fault going, and then later, hundreds of years later, that segment with a neighboring segment and a bigger earthquake. So that's where this result comes out that some of these areas may tend to have more frequent earthquakes, but not as big.
One final question up here.
Hello. Looking at the Dagami maps that they have a GIS and you can pull up different layers and so on, it seems like in the Portland area the biggest risk we have is a crustal quake from the Portland fault. And the magnitude of shaking and intensity and so on of that is far greater than even a magnitude 9 subduction quake.
Yeah. Yeah, no, that's
What's the frequency on that?
Yeah, see, I don't have those numbers, but that gets back to what I was saying, that these giant earthquakes are infrequent, and relatively infrequent in any place. But you're going to have, on average, for every 8, you expect to have 10 sevens in a region and 100 sixes. So the odds are, if you ask what earthquake are you most likely to feel that's going to cause damage, it's not the 9 or the 8. It's a 6.5 that's close to you, and that's true in California. and it's true here. And some of the faults we can look at and get some good information for. I don't have the numbers in Oregon, but yes, statistically, that's the earthquake that you're likely to experience. It's going to cause damage to 6.5-ish close to here.
With that, let's give our speaker one more round of applause. Make sure the ground gravity captures those little dull pencils and come back at the